very high competition, right? So whatever energy system is there, whatever physical is there, I try to mimic on the computer as well. So before my formal presentation, let me give introduction about our IIT Mandi. Hello? Yeah. Fine? Yeah. So IIT Mandi is something located in an unusual place. Yeah. So most of people may have visited to hilly station and all those things and come 1 or 2 days, and but you may not aware about the whole thing. You may not explore the whole thing because you may have gone some tourist place where all facilities are available and all those things. So we are located in a valley surrounded by big mountains. Okay, and it looks like a bird nest. Yeah, we are in the bird nest and Himalayan land. You are used to say Himalayan land. So this is lower Himalaya. We are at 1,000 meter altitude. Okay, generally we don't receive snowfall, but these mountains have received the snow during the winter season. Okay, and look at these ridges. Okay, these ridges are connected. Okay, please remember these ridges. I am going to tell you a very beautiful thing. Okay, if you basically here climb up to these ridges and you can try. Okay, along with that, IIT known for very mental exercise, very high mental exercise. These telling you to give you physical exercise as well. Okay, so on comparison, I may not look like I'm doing very much hard work, physically hard work. Okay, but you little bit walk, you can achieve a lot of altitude. Okay, and we have two campuses. One campus is South Campus. When IIT were realized, then things have started in this campus only. And behind to these mountains, we have another campus that is called North Campus. Main activity happens in North Campus, and this is only way we can travel to around the mountains and go to this campus. But we are basically constructing road to connect this campus on this mountains. We cut the mountains, and next week I may have it. Okay, and this is very unusual establishment of the buildings. Back one is your academic building, then hostels are there, then you have faculty buildings. Okay, so basically we have all things are placed very close to each other, so that learning very closely way of learning may happen. This is administrative building, and this is basically community activities like this is your auditorium. Something is there. This is guest house. This is guest house, and this is the director's room. Okay, director of is mentioned on it. Okay, so this is a IT Mandi, and this is the situation during the clear sky. We have very beautiful sky. This is clear blue. Okay, and this becomes a situation when there is a rain. You see the whole cloud is emanating from the on your from the mountains and rising from mountains. Sometimes you feel yourself in the clouds. Okay, and this although we don't receive regularly snowfall, but once probably in my stay of 10 years, it becomes 10 years, we received snowfall only once. Okay, in 2019 probably. Okay, and this is the situation generally snowfall, fill up the whole snow. Okay, and this is a during night. Okay, so these are establishment of IIT Mandi, if you will there. Okay, and I told you, just remember those phrases. And if you reach, you will track on these ridges. Okay, I did once because some my friends come up with very adventurous. I'm not that adventurous. She encouraged me to let's have a try. If you try, if you basically instead, you can also go that place what I'm going to tell you through this road. Okay, but you also you can track on these ridges and you can reach a very beautiful place and having mentioned in our Vedic literature that is called Parasar Valley. Parasar Muni, it is, you may remember it is having that mentioned in the Mahabharata. Whole Kauru Pandava is that is not the Parasar Muni only. Okay, and his son is Vyas. And okay, and this is located. Okay, this is located around 3,000 meters altitude. So while trekking from IT Mandi, you climb there, remember the previous slide, climb up to the mountain, and then travel up to this. You cover the distance around 20 kilometers, 20 kilometers trekking, and achieving an altitude of 2000 meters in 2 kilometers. Means you are climbing around 650 or 700 floors of the building. Okay, and we did it in 10 hours. We keep on traveling to reach this place. Okay, and Parasame, and this is a temple, Parasa temple. Okay, and people also say this is basically there is a lake, and there is a floating object in it. And people used to say being basically all their brothers were thirsty and there were no, they were during their affair was, they are talking on these places. Okay, so they were thirsty and then we make a fish, put the fish, and then there is a dish there. And this is made by their fish. Okay, so these things are there. Okay, and you know Edinburgh, but this is Manali, I'm coming on that as well. Okay, so along with that, doing the trekking and reaching all those beautiful places, very calm and serene places. So you have other tourist places. While having the activity, you can visit to Manali, just for 10 kilometers. You go in morning and come back. Okay, you have Queen of Hills, Simla. Okay, hardly 1 or 10 kilometers. One of the most beautiful retreat stadium in the world, Dharamsala. Okay, you can see all the mountains with covered with the snow. Yeah, and Sikati Devi, that is Sakti. Okay, that is one temple. And this, the beauty of this temple is that there is no roof on that temple. It is uncovered. And people used to say that although it is very high, you can receive a lot of snowfall. Okay, and this temple will never basically stay. This will never stay on this temple. Okay, so these are the advantages of visiting for activity and working with activity. Okay, I invite all you to visit there and having things. Okay, along with that, our mental exercise as well. Okay, so before, okay, this is about. Telling about the activity, some lab activities. Beyond that, whatever I'm going to my regular presentation, we are doing much more than that. So this is basic. I believe most of the people are from the mechanical. Okay, so these are systems. Okay, everyone is basically related to that. Basic is basically a system for the waste management. Whatever waste is there, we are extracting the energy from that. Okay, so it is a partial combustion we are doing and developing the sync gases and using sync gases for the purpose of energy. Energy is need of everyone. Okay, this is well in the effect of radiation and the gasifier and how sync gases can be increased. The development of the generation of sync gases can be increased. Along with that, this is a kind of open situation. You can see we are simulating a room in the place of sunlight. So there is an optical window here, through which sunlight is coming, and all walls are isothermal, are the same temperature. Bottom wall is heated. Something kind of like heating is this kind of heating is more effective heating, and all the European countries are utilizing this kind of heating. So this kind of sunbeam is coming through windows. Okay, and the fluid flow and the heat transfer phenomena happen. Very beautiful fluid flow and heat transfer phenomena happens in that room. And this kind of system is created, fluid system. Okay, and this is kind of two-through kind of thing. Yeah, fluid system looks like a two-through. Yeah, but this system these are our invented by in our lab. Our students my students have invented. Okay, and this is something we couldn't find a good name for that. And this is basically we used to say that it is a side setting position of person. Basically, someone is distressed and going solitude, sitting in the garden, and wrap his legs around his hand and put head on over it. Something looks like that. Okay, so I didn't get a proper name. Okay, so another is the solar distributed gravity. Many people are knowing that we are utilizing sun radiation sun energy to reflect to mirrors and concentrating on here. This is optical window through which this is going porous media. It is basically dropped here and very high temperature is generated, and further we are heating the fluid here or something through which we are running the thermal power plant, solar thermal power plant. Although we are not going to very detailed geometry, we are basically looking very looking for fluid to heat transfer is that. So we have developed the idealized geometry. And this is a collimated beam is incidentally, something like beam is coming up, but it is incidentally, and further it basically increasing the temperature of the fluid. And with this fluid further utilized to run the power plant to generate electricity. Okay, so these are another work. Okay, so whatever I am going to present, this is performed by my PG student. So I am grateful to him. I am acknowledging him. Okay, so this is outline at my presentation. Basically, radiation, when it comes to radiation, you think many things, okay? Many things, something, gamma rays, this mobile radiation, okay, and X-ray radiation and all those things coming up. All have very large spectrum, but I'm concentrating on the thermal radiation is providing me heat. All radiation does not provide heat. Only thermal radiation providing, but I'm coming on that, okay? So basically, if you have the knowledge of radiation, it has very vast application. You can utilize it as engineering application. You can utilize it strategically, looking at signatures, some signatures. You can make your own decisions. Whole planet of the Earth is owned by three things: your throughput, heat transfer, and radiation. Okay. So you can also work in the climate thing. I have one project on climate tourism. Okay, we're looking to calculate the concentration of CO2 gas, greenhouse gas, and trace gases in the atmospheric column through understanding the radiation technology. Study communication, I'm coming on that. That is very. This is for national importance. Okay, and then little bit equation. Very quickly, I will browse over that. Okay, because it is a little bit mathematics involved, and mathematics is already going. Okay, so and some models there. And then results, I'm coming on for results, combustion and radiation, and blue radiation. And I will summarize my presentation. Okay. So let's look at whatever radiation I'm talking about, that is electromagnetic radiation. Okay. It has very large spectrum. It wavelength basically 10 power minus 14 nanometer, 14 meter means 10 power minus 2, 10 minus 2 picometer. Okay, to very large 10 power 4 meter. Okay, and these ranging from gamma rays, which is very high energy, to very low energy, that is radio waves. Okay, AM, FM, AM, TV, and all those things. Okay, and in between, only pure radiation. Basically, we have our body is sensitive to that. Basically, our sensor used to recognize that one. Something is visible, whereby we see the things. And it is thermal, which we feel the heat. We don't feel the heat through gamma rays, but they have an impact on our body. And FM, FM radiation are around us, but we don't realize it. Okay, so these are basically the range of the spectrum and the different name of that. And what is this spectrum? This is gamma rays is generated by through nuclear reactions. And X-rays, you know, to be generated for medical applications, medical imaging and something academic. Ultraviolet, you have the photochemical radiation and all those things. Visual they also provide heat, the human vision and photosynthesis used for visual light. And infrared, gamma radiation is provided heat. Okay. Other things does not provide heat. And microwave dielectric heating. Okay. I'm concentrating on this infrared radiation, this is thermal radiation. Visible, little bit total visible, infrared, and little bit ultraviolet. Used to say it is thermal radiation. Thermal radiation, whatever we're talking about 0.1 to 200 micrometer. That is the range where we are basically applicable to mechanical engineering. Okay, so it is also categorized in three parts: near infrared, mid infrared, far infrared, and basically emission happening 1000 Kelvin to 2,000 Kelvin. It is belongs to, here it is Beam's law, and Beam's law to the near infrared. And if you want to make basically some strategic things, so you look at gases emitting something different in the different infrared range, and our normal earthly body, basically 3000 to 1000 Kelvin, is directly into 5 infrared. Okay, and these can be seen in the different applications like sun, heaters, and these are infrared. Microwave, sometimes we get heating by microwave, not always. Only water is direct heating, water is sensitive to heating. Okay, so microwave heating, basically we are using it. And laser is used for gas, laser, and cutting and all those things are there. They have a very small wavelength on which we can generate it. Okay, so this is the whole electromagnetic radiation comes to verified person situation. Okay, this situation everyone basically come across and feel very comfortable when they are basically in the winter season. Yeah. So basically this situation has 3 questions. Okay, by which mode of heat transfer you are receiving heat, how much heat you are receiving, and what is source. Okay, so if you able to basically it is you are receiving only through radiation mode of heat transfer. You are receiving heat only through radiation, not another mode. You know there are 3. I believe everyone understands this is the general basic thing. Yeah, conduction, convection, and radiation. Conduction, there is no conduction because there is a gradient temperature difference. There is no temperature difference in air, and also air conductivity is very low. So air is no conduction, no convection because you're not direct facing the whatever basic plane is there. Okay, if you direct facing the plane, then it is convection. It is only radiation. And how much? What is source? Source is this gases. These are gases. These gases are CO2 and H2 and little particles. Okay, wood is basically burning. This combustion is happening. So wood had some volatile gases that get volatile and they will become combustible product and further combustion is happening. Okay, so here it is combustion that it is fill up the gases of CO2, H2 and CO. Okay, and some other gases are also there and they are emitting the radiation. Not through wood. Wood basically, wood it is in paper liquid. Wood is not giving burning of wood is not giving the energy. It is just gases is giving the energy. Okay. Now how much it is basically Q is coming into factor, you calculate the factor, you can get it. And suddenly the suddenly flame becomes big, you feel more heat. What you will do? You go back. Okay. So what you are reducing W factor. Okay. So if you are able to basically answer to these 3 questions, then you can give a solution to steam engine system, steam engine problem. Okay, one is everyone has seen launch of the rocket. Okay, so basically lot of hot plumes, that is very high temperature and pressure, is emanating from here. Okay, and the provided thrust. You may be amazed that if you take a solid, it does not float. Okay, where what you are trying to do, using that air, you are trying to push the whole rocket upward. Okay, so you know how much powerful this plume could be. So it is very high temperature and pressure. I'm coming on what temperature and pressure on this plume. And also this is heating the rocket. Look at heating, upper base stream. So then it is upstream of the rocket place is upstream of the plume. So only mode of heat transfer is heating is radiation. Radiation is only going backward. Convection cannot go it. Okay. Another thing. Look at the situation after some operation of this rocket. Okay, whole thing are not burned. Okay, very high temperature and pressure. And you know this is the gas turbine. Yeah. So it is I believe this is a more fascinating, complex and futuristic machine ever built. Okay, and it is operating in very extreme conditions. Okay, so this is similarly kind of thing. And you will be basically surprised that our country is unable to build any gas turbine until now. We are importing it. You know Tejas. And these are applications, industrial application as well as aviation application. Fighter jets and everything having this kind of engine. You may be not aware, yeah? Tejas has this kind of, all fighter jets have engine. But Tejas, you used to say Tejas is our product, yeah? But engine is not our. So long back in 1985, some project, a very ambitious project I started. The name of that project is Kaveri. How many of you are aware of Kaveri project and Kaveri engine?
Yes, that is a cryogenic.
Cryogenic is different. Cryogenic is for rocket. It is for ISRO. It is for DRDO. Kaveri basically, government has started to build the gas turbine engine, 1985. It becomes 40 years, we are still not in stage to make it successful. Okay, and we are importing the engine for our Tejas from the GE. We signed MU with GE to provide the engine. Okay, still this become in between. People realize that you cannot make it put into the world box. Then, but this government again pushing it that we should develop it. And you may also remember, either you heard or not, that PM speech for this Independence Day from Lal Killa. He said our country should have everything. We don't have everything. Everything because it has very much know-how. Okay, you cannot do it with a small thing one of this. If you're able to do it, then this know-how or this knowledge can be utilized to develop many things. Okay, it is rotating very high RPM. RPM I don't know, but it is 28 bar pressure, 28 to 40 bar pressure. Temperature is 2000 Kelvin. Okay, and this the operating condition, if you're rotating something, then you look at how much material it will be released. Material may be there. Okay, and also how much the thermal and mechanical stresses will be. Mechanical and thermal stresses will be negative. If you will manage all those things, then you can do many things. Okay, that's why this project should be successful. 40 years. Okay, then. Okay, so production of the fire safety equipment, whole radiation, energy or radiation through the radiation. Okay, these are the extreme injuries. Okay, and we should develop our capability. We should develop first humanly, our being in academic, our main responsibility to develop the human being, yeah? Human being or something, develop the student. So the students should we pull up their socks and faculty should also pull up socks so that give the challenge to them to involve in all those things and make it successful. Okay, this is extreme engineering applications. Go for the surgery application. You may have seen this situation. Yeah, in movies, practically you may have seen it. Okay, so basically, if adversaries is your territory, you fire the thermal-seeking missiles. Okay, you need not do anything. You have to build a system in thermal-seeking missiles that detect the enemy plane and chase it. Okay, so depend upon situation. Either it hits jet, or jet can basically double it or make it full and can return to the territory. Okay. It is not a very easy thing. Okay. So based on it has some signature. In signature you can detect it. Signature is IR signature, something like that. Thermal-seeking missile. Okay. So because the thing is that this jet body and this flue. Okay. Flue having the CO2 gas, they emit in certain wavelengths. And this wavelength you can recognize. Okay, some signature is coming from CO2 gas. Then you may realize that something burning up. Okay. It could not be bored and anything else. Some combustion is happening. Combustion is very man-made machine. Okay, then you realize that the man-made machine is our or enemy. Then you can fire this thermal-seeking missile. Yeah, using this characteristic, you can build a lot of smart weapons have been made. That are man-made. Okay, man-portable air defense system. Okay, you on soldier you can fire. They work on the principle of the fire and target principle. You just set a target, fire it, and injure. Okay, using this, Ukraine using all those things to defend against the mighty Russia. And till now they are defending. And these kind of systems, Ukraine does not have Western countries providing this kind of system to Ukraine. So that till now it was more than 3.5 years in Ukraine. Still, Ukraine able to defend its territory because weapons were supplied by European or Europe or US. Okay, these are all the geopolitics. So we should have no one is going to give this weapon. They are going to give you weapon. They are not going to let a symbol. They are going to ask you. Okay, you should have a knowledge for all those. Okay, so basically when start from thermal-seeking missile is changing you, you have some defense mechanism. You eject the flare. Yeah. So flare is made of some Combustion of some different material, MPP, that is magnesium, Teflon and fluoride. MPP, we don't sorry. Teflon and, okay, first time also here I also get surprised. Teflon coating we know it, okay? And Eton, I don't know which kind of material it is. So it basically it emits a lot of radiation, which basically confuse this combustion crystal. And this way you can protect your jet. Okay, these are the things. This is a strategic application. Second application of radiation heat transfer, if you understand radiation. Third is whole climate. Okay, sunlight is coming. Sunlight is coming, lot of things happening. This is reflecting, absorbed, then emitting, then you have a CO2, H2O. Okay, presence of CO2, H2O making this planet conducive to living environment, living temperature. Basically, if CO2, H2O is not there, although CO2, H2O are blamed that they are greenhouse gases and changing temperature, but till now they have been maintaining temperature which is conducive to our living environment. 25 to 30 degrees centigrade. If they are not there, then basically all radiation will be go to deep space and this current becomes very cool and it will not be good for living. So this is also using radiation concept. You can do the energy balance and you can see that how much temperature will be rising. And you may hearing that if carbon percentage will increase up to this one, then the whole planet will be basically warm up and glacier will be melt and all those things. Something you may be hearing, yeah? Something is coming up. Because of these calculations, it's telling you how much energy balance is there. Okay, so we are taking that there is no much carbon emission, carbon dioxide emissions will happen. What is the percentage of carbon dioxide in our atmosphere? We surprised it is. Anybody have an idea? Our atmosphere is made of many gases, but the percentage is drastically different. Yeah? How much is N2? How much N2 is there in our atmosphere?
78.
79. 79 gas. Some both fractions are one fraction. 79. Oxygen?
21.
कितना हो गया? 79 plus 21.
100.
Then you have very scope of CO2. Along with that, water vapor is also there. Okay, organ and all those things are very less percent. And what is percent of CO2? Take it. I mean, 0.0. Yes, 0.03. It is just 0.03% carbon dioxide is there. It still is blamed. Other gases are not blamed.
No.
Okay. And how much is water is there? Water vapor? Based on humidity. Based on humidity, yeah.
Climate condition.
Yeah, तो कितने परसेंट करेक्ट तभी 100% ऑलरेडी हो चुका है हमारे से ज़्यादा जा रहे हैं 0.03 का ऐड कर दिया वाटर ऐड कीजिए कितने परसेंट एनी केस एनी वन 3 to 4% कुछ एडजस्ट हो जाता है ये ठीक है 3 to 4% 3 to 4% वाटर वेपर है
3%.
हैं
3%.
और 3 to 4 वेपर बोल दिया हाँ 2 3 या 3 to 4 2-3% ही है 2-3% ही है
2-3% है.
2-3 है कभी-कभी 4 भी हो जाता है वो जब हाई ह्यूमिडिटी हो गया
वैसे 2-3%.
2-3% ही है
कोस्टल एरिया में ज्यादा है।
हाँ तो वही तो इतनी परसेंट ही है तो ग्रीन हाउस गैसेस है CO2 and H2 and H2O ठीक है इनकी परसेंटेज कितनी है 2-3% ही है फिर भी ज्यादा है एंड लुक एट हाउ बिग इज द सिस्टम ओके उसे बोलते हैं कि अगर 0.03 है अगर 0.006 भी हो जाएगा it will be disaster. Okay, but look at percentage is very. That's why Trump is saying that this whole climate policy and all these are just thoughts. Okay, because this percentage is very low, but it's not understood the implication of this. Okay, whole climate policy and all this he is spread when you compare some Paris convention and all those things. He just spread everything, right? He just created right and all. Some jobs is coming. Okay. So, but it's so much. Even competition is so much, it's still digital. We point to people. Okay. But it has a strong implication. Okay. So this is a atmospheric, these are from the far field concept, if you understand far field. There is concept of near field, okay, where Planck itself is said, all these are done by Planck's law, okay. Planck law said that when object between these two bodies is less than wavelength, method, okay, then basically you can state energy this Evanston wave, okay. The traveling of the Evanston wave happens, and that Evanston wave has energy some wavelength greater than 60%, 60 times, in by method you are calculating the part wave, okay. So basically, if you combine this thing, if you develop material, okay, material and drive in such a way that you can also basically tune its emissivity, okay. So you can tune in such emissivity that it could emit the radiation in 8 to 30 micrometer. Our atmosphere is transparent to 8 to 30 micrometer wavelength. Window is there, okay, there is no, gas is not stopping anything. Whatever energy you will make, it will go in deep space, okay. So if you tune in such a way that more emission happen, 60 times what I was saying, into 8 to 13 micrometer, then basically you can send all energy to deep space, okay, and you can cool this place if you basically make a coating of this material over this building. Without, you can cool this place below the atmospheric temperature. Without AC, you can do it, okay. AC, that is not radiative cooling. It is not radiative cooling. It is not radiative cooling. Okay, you can achieve a temperature below the atmospheric temperature. It is very difficult. You can only get through AC and refrigeration only. Okay, so basically, if you are doing this one, then basically you can bring ice age again on the Earth. Okay, you can send all energy to atmosphere. Okay, so this is just like it is not possible because this is nanotechnology. Okay, and material and all those are very costly currently. Okay, but yeah, who knows what you're going to happen in the future. These are future statements. Okay, but I'm just selling my field. Okay, nothing else. Okay, so okay, so if this radiation is so much important, why there is no much work? I'm not saying minimum. I asked many persons to collaborate and help me to develop all those things, but there is nobody come forward. Okay, so basically it is whole radiation is burden of misconception. Okay, I'm talking about medical thing. I'm not talking about radiation. Okay, so basically there is a mix. The radiation is only important at a high temperature. Okay, but this is not true. If you natural convection is happening, radiation is always important. And radiation is more than the convective heat transfer coefficient. Convective heat transfer, again, people may be knowing. Okay, so convective heat transfer is look at the convective heat transfer coefficient. If I calculate similar the radiative heat transfer coefficient, convective heat transfer, radiative heat transfer is always higher at lower temperature difference and almost equal as the high temperature difference. So you cannot say that convection is happening and radiation is not important in low temperature. In natural convection is always important. Okay. Oh, something? No comprehensive course in economy? Yeah? So barely 1 or 2 weeks on the radiative transfer. That too end of the semester. By time faculty and students both are on the pressure, end semester pressure. Quickly you have to just cover the thing and no deeper thing. Concepts are limited to surface of the radiation. Gas radiation, particle radiation are not being covered. Okay. Emission from gases and particles, it is totally different concept. Okay, and easy to be available. Okay, if you're going for instrument, it is very costly instrument. And image concept is also very costly. Okay, software is also not available. The concept of somewhat unknown, which we don't hear in very frequently. Okay. You may be seeing the CO2, H2, CO are participating gases. Participation gases. Till now, this word may not have, you may not be here till now. Participating, yeah. So, and when for the non-participating gases, I tend to go to those genetic molecules. We are going up to the structure of the molecules. Okay. So, do not contribute in the radiative transfer. They are transparent gases. That's why our atmosphere is having them. Only CO2, H2 are great. And we are looking to establish the colony on the Mars. Yeah. Some great effort, great project is going on to send a human on the Mars. How many of you are aware? Some American company and America and European are looking to colonize the Mars. Do you know what is the Mars atmosphere? What is the pressure and all those things? Sometimes people are saying they got the some opinion that billions years back Mars has life, but it is not life. Okay, something that everything about it. Okay, now Elon Musk, you may be aware, yeah, Elon Musk and all people putting effort to send the humans on the Mars. And Mars probably its pressure is not 1 bar, it is very less pressure as to transfer. And mostly its atmosphere is made of the carbon dioxide and methane. Okay, I don't know how to do all those things. Okay. So these are the things are there. Okay. So look at emission for gases. Emission for gases and particles. Okay. So particles also means whatever we are talking about something that Delhi during the winter season having very bad weather because of it is happening because whole desert sands are basically floating on the top of the Delhi. If you look at location of Delhi, Delhi is all cut. So it is not allowing the radiation to come on the surface and make it heating and something like that. Okay, so particles are basically its emission is continuous. Okay, although I am taking some other thing. Okay, however, if you take the gases like CO2, we have to take the emission from individual gases. It comes up to the structure of these molecules. Okay, so CO2 is linear molecule. Okay, and whole energy combustion basically we are releasing getting energy from energy stored in the molecules. Okay, because the breaking point. Whole energy, look at whole energy business. The energy is, as my understanding, energy is only located in the molecules bond. Okay, we break the energy, then we break the bond, then we release the energy from there. Then we utilize everything. So energy is there already. So CO2, it is linear molecule, it's vibrate, rotate, translate. So that's why it is thing. And it only emits a certain wavelength, not all wavelength. And this wavelength is very, very problematic. 4.6. Okay, although this is 50, something 2.6 wavelength is also there. But 4.6 is very strong battery of the CO2. Okay, and S2 is not linear molecule, it is triangular molecule. Okay, so vibration, rotation is totally different. And it is emitting lower wavelength and it is emitting higher wavelength. So these, look at the characteristics totally different of all these. And exploiting these characteristics, you can take a lot of decisions. And along with that, when it comes to energy, that is a totally different thing. CO is subsystem of CO2, you can say here. So it has mostly emission in one band. Okay, emission basically is plant function into absorption coefficient. I am coming on absorption coefficient. Okay, so if you come into radiativity transfer, you should understand how much the heat transfer is happening through these bands. Okay, it is not convection. Okay, and look at little bit equation because instrument is not available very highly instrument. Okay, so and we also don't know how much is the important is. First, we need to develop our intuition and tell that is important. Then somebody would be happy to support us in terms of the instrument. So basically, look at radiation participating. What is equation it is? Let's say a laser light is going through a medium which is having the gases and particles. Okay, and you can laser means one monochromatic light, one wavelength light, or you can further you want to imagine it, you can say that you are driving your car in a foggy environment. Headlight is going away, there is very dense fog. Headlight doesn't go far distance, it is there, you can say. And fog is, you can say it is participating medium. Okay? So what then a headlight basically has many wavelengths. You can come to laser. It is monochromatic light, it is single dimension. I'm talking about single dimension. Okay? So it absorbs. Why you are not able to see it? Because it gets absorbed in the fog. Good light is get absorbed. It can emit what a fog temperature is there. You know, any object above 0 Kelvin temperature emits the radiation. Okay? It emits. It all the scattered these particles there, they can scatter radiation and emit again. okay, depend upon the wavelength and particle diameter, particle size also. In static, is that a raw direction to this direction? Whatever direction is, we are considering it. If you consider all these four phenomena, then the equation is developed. That equation is transfer of energy in single direction and single wavelength. That's called radiation transfer equation. This is integral differential equation. S is direction. S is direction. Okay. And there are some variables, some variable dependent and independent variables. I'm not coming that. Now you need to solve this equation. This is integral integration is also there, differential is also there, some complexity is there. So now absorption coefficient, we need to look at absorption coefficient of CO2, H2O particle, everything. Then that can be fed into it, that kind of energy can be transferred. This is the transfer thing, okay? This equation is transfer energy from one location to another location. Okay, finally, I'm only interested how much, being engineer I must say, ShriRam Group does not belong to category of engineering, because engineering is something which deals with the solid objects, solid materials. Okay, we are dealing with gas and fluid. Okay, although they are giving impact to the engineering system, but it is important, integral part of that. That's why we are interface between the science and engineering. We are understanding from nature. Everyone understands nature, but nature and climate and all those things is happening. And we are, whatever effect is coming to this thing on the solid world, we are providing to engineer. And engineer can build it. That is how we are doing. So basically, from all these gases and molecules and gases and particles, whatever flux is coming, I will provide it on the wall, and engineer use this flux to do whatever they want to do. Okay? So this flux is calculated once you get the intensity. Okay? So let's how to solve this equation. Literally it is very difficult. It is not possible at all. Okay, so computationally we can solve it, and the numerical method is that somebody working safely, they may know that how to resolve the gradient. In fact, medicine also know that resolve the gradient. Okay, the gradient is basically difference between these 2 points divided by the distance. Yeah, that is a very basic of the calculation of gradient, and distance between very less. So basically, we put this kind of a grid in the system to resolve the gradient, because gradient is coming and direction is also coming. Along with spectrum is also coming. The three contributions are mediated. So basically, CFD people, okay, use this kind of a grid to resolve the gradient. So CFD is all about resolving the gradient. Okay. So they are resolved to put this kind of grid. And to resolve the direction, we are using this stable coordinate system, where polar and azimuthal directions we take it and we get all directions. So basically, we need to define this direction at each and every point in there. And you taking one direction, this one, to set our radiation. And you know, the radiation basically, energy does not transfer between wavelengths. One wavelength energy does not transfer, and one direction to another transfer does not transfer. So you cannot transfer energy between the wavelength and between the direction. So you have to solve all directions, all wavelengths. How many directions? If one object is there, it is emitting out 4 5 directions. How many directions? As much as you need to do the lot of experiment, that's why my guide is numerical experiment. We don't do the physical experiment, we do the virtual experiments. So around 100 directions we may get to resolve the whole directions, or you can get the accurate result. 100 directions, and how many wavelengths? 100 of millions of wavelengths are there. Okay, so this equation is that much big monstrous factor, you can say. It can eat up, no computer technology has made till now to solve this equation for any engineering systems. Okay, so we do the some modeling to reduce the compression cost. Okay, so look at this equation. This equation having the absorption coefficient. We need absorption coefficient. Okay, and absorption coefficient is similar. The absorption coefficient variation is similar to the emission photograph I've seen. I've shown you. Okay, so this is also absorption coefficient. Okay, and in this absorption coefficient is dependent on thermodynamic state of gases. Thermodynamic state is temperature, pressure, and mole fraction. Okay, so look at combustion system is happening. So the pressure may be on isomeric situation is there, but temperature and mole fraction keep on changing. So you need this kind of a thing. Although variation will be almost same, but value will be different. You need each and every point you need a thermodynamic state of the vessel. So S2 is the emission is more water graphite. I've shown you. The emission is more on lower wavelength, but look at adjust coefficient is more on the high wavelength. Okay, emission is adjust coefficient into the Planck function. Planck function at this temperature becomes very high at the lower wavelength. You know, these when temperature keep on decreasing, your C is keep on shifting towards left. Okay, so this way happening. And here is CO. CO is same. Okay, so these all could be feed into that equation to solve it. Okay, so and if you try to solve this way, this is called time-by-time method. That is used for only benchmarking method, and but we cannot solve it. Okay, so look at the property of that is gas particles. Particles basically variation of adjustment coefficient is continuous, unlike to the gases. Gases are discrete. It is unlike gases. And with the increase of the, and this depend upon the particle diameter size, we are taking very simplified way. We are taking particle as spherical only, although they are not in spatial. So spherical with different diameter, the adjustment coefficient keep on decreasing with increase of the particle size. Whereas particle poses another parameter challenge, it also scatters. We also need to know what is a scattering coefficient. It depends upon the wavelength of particle diameter and the wavelength of the light. Particle diameter, wavelength of light. There is no clear trend is there, but along with that, it also scatters. It scatters is going, and which direction is it scattering? We also need to understand it. And this is a scattering phase function. Okay, although isotropic scattering happening when particle size is lower to the wavelength, but when it is become particle size becomes big, then there is a low kind of thing is formed. Okay, so this scattering is another kind of challenge is posed. Okay, so include all these things. Okay, so okay, probably okay, so after all this change it a little bit further development. Okay, so when basically you being engineer, you not only concentrate on one mode of heat transfer, you need to all modes of heat transfer. Conduction, convection, radiation. So then your temperature equation, this part is, first part is convection, then conduction, and third part is radiation. Radiation will come into part. And finally, this part, last part is calculated by this equation. Once you calculate it, then okay, so you calculate it, then how to do it? Okay, so first simplified way to do it, to get only one absorption coefficient around the wavelength, you will remove the wavelength. Okay, so we integrate over whole wavelength. What is not working? Something, okay. So we consider the first, we will calculate. Okay, so basically you can get only one absorption coefficient. And you can, in this way, you can reduce the compression cost. This is the whole purpose to reduce the compression cost. Okay, probably all things are not coming up. Okay, another is basically, that is a very inaccurate model. Another model is that this kind of absorption coefficient is happening. Okay, this one, last one. Okay, you can transfer in some other domain, it becomes monotonically increasing graph. And you know, integration over this graph is very easy and also accurate. Okay, when it gets accurate, then you can solve it. Okay, so I'm not coming here. I'm not going to detail out that. If you're interested, you can come. I can teach you all those things. Oh, questions are not working. Okay, then suit is also formed. Suit is also particle, and this is suit is basically incomplete combustion, which is also causing a lot of problems. So you can also get the absorption coefficient and how to use it in your equation. We did it. Okay. So let's come with the first problem. That is academic problem. Okay. Academic problem is always a small problem, simplified problem, so that we can learning could be happen properly. Okay. So this is a tank combustor. Tank combustor is basically very simplified form of the gas turbine combustor. Okay, and whole purpose of gas turbine combustor is that it should be basically combustor should be as small as possible. Although it is heart of the engine, but it does not find a place. Okay, you put compressor, turbine, everything together, whatever things are remain, then you place the compressor, and you design compressor in such a way that it should be very, very small. Okay, so flame should be not big. To reduce the flame, there is swirler is there. Primary is coming, it is swirling. It is basically not direct injection that object, it starts swirling in it. And then you, through this black thing, you inject the kerosene. You kerosene, and then it will start combusting it, start burning it. Okay, and this is the operating condition of this fan combustion. When you understand the whole phenomena, the same phenomena you can apply for the gas turbine. Okay, so this is the swirling flow is happening, and very high swirling is happening, and low pressure flow is formed, and fluid is fuel is trapped into this small zone and burned it here. It does not go beyond that, and there is a and there is a secondary flow as well. Secondary flow, the same temperature is around 2000 Kelvin, and no metal can temperature sustainable 2000 Kelvin. So to protect the wall, we basically inject the secondary flow so that flame should not reach up to the wall. Okay, so swirling flow is there, and this is the temperature is being generated. So temperature, look at combustion is happening very small region only, and temperature is reaching around 2150 Kelvin. 2150 Kelvin temperature is there. 2100 Kelvin temperature is there. Okay, without radiation, I not place the radiation. When you place some very crude model, which is inert model, is basically it reduces the flame temperature drastically. It reduces from 300 Kelvin it reduces. The role of radiation is that it takes the energy from very high temperature zone and places low temperature zone. That is the whole role it does it do it. Okay, it will do it. Okay, so basically it reduces temperature, and look at SLW, basically it is more separate model, and it is giving relativity. Temperature is basically it is not reducing the flame temperature that much. It is just reduced, and WCC model is also available. It is included. It is also reducing a lot of temperature. So these are based on accuracy of the model, and then the level of temperature is reduced. And look at the radiation, because radiation depend upon these species, CO2, H2, and mole fraction. They are only limited into mostly the primary zone, secondary zone, and all those things. Okay, and it is telling this is radiation source. It is telling radiation is energy is removed from this region and placed in this region. And whatever energy is does not remain, it placed on the wall. That's why wall have two kind of flux. One is convective flux and another is radiative flux. Okay. So in this way, some flux will also available on the wall. Okay. Heat transfer phenomena. Peak temperature is reduced due to this model. Depend upon accuracy of different model. Peak temperature one is basically around 2000 Kelvin to around 1750 Kelvin. Okay. So and other model is further reducing it. In this way, different model is reducing the different level of temperature. Okay. And outlet temperature is also changed. Okay. In this way, depending on accuracy of the model. Okay. This is the heat transfer performance. People used to say that radiation is not important, it is only 10%. Even who is involved in research kind of a thing are very people. They always discuss that radiation is only 10%. Look at it. Okay. If you look at total, here total is without radiation, it is 299 watt. Okay. And if you go for this accurate model, 322 watt. Okay. Only 22 watt has increased. It is 8 to 9%. 7%. 7 to 8% is an increase. Okay. By this way, they discourage that radiation is not important. But look at it. Internally, convection has reduced. Well, it is becomes small. 299 watts, 151 watts. Okay, reduce the one. And radiation is 171 watts. So internally, because radiation homogenizes it, so whole convection depends on gradient. Gradient has reduced. So radiation is more than convection. However, in total, it is 78% only. Okay. In this way, people only looking at the final thing and making conclusion. And conclusion is wrong. Okay. So this is the heat transfer performance. Okay. Come to Kaveri. okay, I received one project from DRDO, and till now they were not aware of Redison model at all. They are doing big thing and they have responsibility to develop the gas turbine that is corrugated. Okay, but till now they have software, they are running, they have big nodes and all those things, but they basically not aware of the Redison model till now. So we have developed all the models, provided them, and their system so much big that I am not able to run with my system. You know, whole combustion is always a complex field, very complex field. Radiation is not less complex. So they have provided fluent side. I'm not aware about the fluent software. Very strong software. Okay, solving the two-plane transfer problem very accurately and provide the results almost expert the result. It is thoroughly validated. It is not only validated in India. It is worldwide is validated, and most of the researchers are using this software to do the research. Okay, it's just thoroughly validated throughout the world, and they sell very cheaply to academic, but industry it is very costly. Okay, so basically they are basically developing the habit, or they are basically what do you call it, bad habit they are developing in academic, so that person will go and use that software in the industry. That is how happening. So they are selling one node, one license, perpetual license. Do you know what is the cost? Of learn software, it is 1 lakh only. And do you know how much they sell for the industry? Same license. For only 1 year. They sell it is perpetual. How much? And one license, what is the cost of one license for the industry? Same license which we sell in academic. It's just 1 lakh. 1 lakh, and yeah, if you take a package of 25 lakh campus per year, 25 lakh investment. But same package if they sell to industry, do you know what cost they charge? 40 lakhs for 1 year. 40 lakhs. Okay. Next year you have to take again 40 lakhs. Nothing. That is industry. That is academic.
Number of nodes were.
नहीं कुछ नहीं, कोई नहीं, research license लेंगे, same thing you can do here, because they are making money out of it.
42 lakhs.
Yeah.
Single license.
हाँ?
What a single license.
For single 40 lakhs, हाँ अभी तो और बढ़ेगा वो, मैं बहुत पुरानी बात कर रहा हूँ. That kind of that 1 lakh per academy, because you know this is not a profit organization, they are not making business out of that. Okay, you are just paying to them. Even developing the bad habit. If you take the student to on this software, it will go to company, they will monitor. This is their business model. Okay, 40 lakhs for one license.
Students are doing open source, they are also developing.
Open source, okay, initially I have also started with open source. When I returned to academic, I thought I will develop this kind of hybrid, this kind of training to students so that they could go company and start the open source thing. But look at how many man hours they have put in. And they have very high aptitude students, okay?
Yeah.
They are developing it. That manpower you cannot use in the open source. Open source, you can encounter any kind of bug, and nobody is there to resolve the bug.
Yes.
Okay, I have started it. And also, if you basically even academic, people start questioning it, because learning curve is in open source software. Learning curve is very long. Okay, you should. To learn it, you should know that when a bug is coming, you should know the programming, you should know the algorithm, you should know data structure, memory architecture, and all those things. Okay, computer architecture, so that you can run it. These and all those things. Anytime a bug appears, you can get it. Okay, you cannot solve it.
Just one challenge.
So many, that's why they will say it. Even I trained my many students on the open form. Okay, I didn't show those problems. Okay, and that person also went to join the company. He was basically advocating to do having the open source, but management was very skeptical. And also, that is one aspect that the supporting is available, whatever is coming, supporting will be able to resolve it. In this way, they can make a business. Pentair is, I'm talking about company. Pentair is compact compressor, very renowned companies there. Okay. So, and management also, both management are talking and they never allow you to use open. Okay, there are multiple things out there. Okay. So, open form we can use it in academic only. academic only, to training would be very intensive, very good for the student to learn all those things. Here using software, just clicking button and you don't know what is that. But when they encounter the bug and all those things, they're resolving it, then training would be very good, very good to learn. But management should be aware that we are saving the money and we are building the character and building the nation. Okay. But even IIT, people question mark. I suffered a lot. Okay, I started with open form only, and it's going to take a lot of time to learn and produce the results. Whatever the group meeting problem I showed you, that is produced by the open form only. Okay, that model has been developed in open form. Okay, but it is not human element. No one support of that. Okay, so and they have basically captured the market in such a way. Even ISO, DRDO people blindly using even BAS, blindly using this plate. They blindly rely on this software.
Validation results are there.
सब कुछ available है. Worldwide is tested. Whole universities look at people coming from universities, whatever the top ranked universities in world, they are coming from different body. Okay, so it is there. Okay, so Kaveri compressor. So this is a whole Kaveri engine. Okay, and you have compressor, you have electric turbine, everything is there. And when you place everything, people used to say, first priority get all the components and least priority get the combustor. It is endless combustor. This is endless kind of thing. Okay, whole thing is there. There are multiple injectors through which you are injecting the fuel. Okay, so your design of this combustor should be such a way that it is very high intensity because you need a lot of thrust. Okay, and should be but it will minimum space. Okay, this is design of a 20-degree sector of the combustor. You can rotate it to 18 more, then it will be 360. Okay, so 18 as an injector through which kerosene fuel is injected or jet fuel is kerosene fuel. You are using the kerosene fuel, yeah? Jet fuel. Okay, injected and combustion is happening. This is liner. There are many holes on the liner through which you are able to the air is coming after the compressor. And you are dividing this air in two parts. One is going upward up of this one, and something is coming inside. Here the combustion is happening, then you further is going outward. Okay, so there is a primary zone, there is a secondary zone, something kind of thing. Okay, so this is yeah, 20 degree only. You rotate it, it becomes 360. 18 more, 18 injectors. I am just taking one injector. This is injector. Through which fuel is injected. Okay, there are 18 injectors. Okay, so fuel were injected through 18. This is just 20 degrees. Okay, because okay. So when they are providing this file size was 2.4 GB. When I basically included my radiation model, file size becomes 108 GB. That much high comparison cost is there because you need to solve each spectrum, each direction. It's tremendously you have to increase. That's why people are not touching in the radiation spectrum. Okay, 2.4 GB to 108 GB. Now this software will start giving you problem because this file is not getting read again. Because
code is 8.8 GB code.
Code means data file. Because you need to describe it and what I was saying. Okay, 108 GB file. I is not able to read it. There is IO problem. Then I gave a whole code and data to them, run it. They run on their own system. I just am showing that these results are not accurate. But to show you this is spectrum. Okay, and these results are not right at all. Okay, because we didn't run it completely, and whatever the combustion model are also not accurate, whatever they are for it. I have given the code and everything to, which laboratory is responsible for the covering it. There are many laboratories of ISRO. Here, there are many laboratories, yeah. Which laboratory? GTI, Gas Turbine Research System. It is in Bangalore. Yeah, GTI. Okay. So here I written it. Courtesy to GTI DRDO. they are providing. Okay. And this is combustion. This is S2 mole fraction, this is CO2 mole fraction, this is a CO mole fraction. Basically, whole combustion is happening primary one. Then through this hole, the air is coming inside and making dilute. Okay. Temperature control, and biggest problem is that we don't have a testing setup in India for this engine. They are developing engine and they are testing it in Russia. This result is from the Russia. Okay, they are developing anything and sending to Russia for a test. Okay, this is basically thermal coated paint is there. Thermally coated paint is there. Based on the temperature developed here, there is a basically it changes color, based on that you can have the temperature. This is liner temperature, outer liner temperature, and almost these are almost matching. Somewhere hotspot or there something we are able to capture it. Okay, this is a inner liner. Okay, and this is the probe measurement inside the liner temperature. Okay. Okay. Case fertility problem, another problem, issue problem. Okay. So basically we are looking to simulate this kind of situation. Very high temperature and pressure. Plume is coming. Okay. And this is this is a engine, and here base plate is placed. Base plate are not going to simulate this problem. This kind of this kind of a compressor domain we need to develop. Okay. Okay. This kind of this is basically nozzle. This is a outer atmosphere where this plume is coming out, and this is a rocket hole. This is base plate where this place is here, and there is some conditions are there. Okay. So similar to this one, this is the operating condition. The pressure is 2 not 2 bar. Okay, and we are simulating at 3 altitude, sea level, mid altitude and high altitude, 28 kilometers. You know, through altitude the pressure keep on changing. Okay, and pressure, what is the pressure? The ambient pressure is 1 atmosphere pressure, 0.11, mid altitude 0.11 atmosphere, and 0.01 atmosphere pressure at the high altitude. Okay, although we are not changing the difference in temperature. Okay, and some flow is coming. Okay, so this is a simulator result. Basically, whatever is happening in a real world, we are able to do in the computer. So this is a very compressed flume, okay, and flume get expanded at pressure, outside pressure decreases, and further flume is further get expanded, okay, and this flume is basically achieve 8.5 Mach number speed. 8.5 Mach number you understand, huh? Yeah, it is speed of sound, relative to speed of sound. The speed of sound is 330 meter per second, around 1200 kilometer per hour. Yeah, 1200 kilometer per hour. Uska 8.5 times speed is there. That's why you will look such. Okay, and how much temperature? 300 kilometer pressure. That's not high temperature pressure you need to handle that. Okay, this system is very good. Okay, so that's my temperature pressure they are doing it. Okay, so we are able to simulate it. Okay, so this situation is there. There is a entrainment of the air inside the plume, and some bubble is generated. This bubble is having on the heat transfer performance, having effect on heat transfer performance, and mid altitude such kind of bubble is not there. And high altitude this bubble again generated, but atmosphere becomes very, very thick. Okay, I'm finishing it. Okay. Okay. So look at temperature by different models. At sea altitude, your 900 Kelvin is there. Okay, we maintain temperature up to water pressure at 900 Kelvin. So something is there, and due to difference of bubble temperature it can decrease, and further temperature is increases, and original temperature is around the base rate. At the sea level, high mid altitude, both models performing totally different. Okay, SLW is more accurate, and this is SLW, and this is a plotting, and high altitude. Although the trend of both models is same, but they different of limits. Further, we are basically ISRO is taking is redesigning its rocket. They are going for the cluster of multi-engine system like SpaceX. How many of you see the SpaceX rocket system? No, I've just seen YouTube videos are all there and look at they are basically challenging whole physics. My God, what SpaceX? I don't know how he managing that with money. Okay, and he becomes the richest person in the world. His assets valuation is how many do you know? How much he has asset? $500 billion. $500 billion. He is a single person. He is basically breaking all the myths. Look at Rocket. 11th version of Rocket is going to launch on Monday. Okay, they have. ISRO is only looking for the 9. Yes, 33. Booster. भयानक तरह का है, ठीक है? Okay, so इस तरह का एक building है, but now ISRO is also competing on that. Okay, you know the ISRO is basically having a lot of success stories, yeah. And we are in two country. We have done a good project, good missions, yeah. Do you know that how much is our contribution in the world space activity? Despite of so much success stories, what is the percentage of our contribution in whole space activity? Anybody guess?
We don't have idea of a percentage, but yes, we know there are operations that
Yeah, only 3-4 countries will reach the Mars, landing on moon, only 3-4 countries and all those
we
things.
was the first country.
Yeah, a lot of things are there. But what is percentage? This one good success stories are there. The percentage should be some respectable percentage should be there. How much percentage? Anybody guess?
Around 25 to 30.
40%.
Any other?
10 to 15.
Any 10 to 15. Anybody guess? There is no question for the guessing. Okay. Any?
Around 50.
Around 50. Anyone?
2%.
And this statement is made by Dr. Somna. I think that's not one previous chairperson. That's why this government is opening the space sector for the private company. Just 2%. He said our activity is just 2% of whole world's space activity. Okay. Look at how much potential we have and how much we need to do it. Okay.
But they are few countries to successful in the satellite specification. They are
ये just news है बहुत सारी यूरोपीय कंट्री बहुत अच्छी कर रही है
So in relative to the European countries,
ये not whole world activity whole world activity how much is our country okay सिर्फ 2% ठीक है so that's why he is opening this government has opened the ISRO facilities for the private. They have changed the whole policy. Okay. So I'm also involved in one other thing. अभी re-entry vehicle नहीं बना हुआ. Okay. ठीक है. So this kind of they are looking at. Also they have given me money concept today. And biggest problem is that even Somnath has said one thing which I didn't like it. They said that earlier we had very close collaboration with academia. We are doing a lot of projects with academia. Later they came out of that. This means they want to say that now they have more knowledge than academic and we don't need it. Okay, project उनके अभी से project नाम project नहीं देते और उनके project का एक concept है if you are going to take a project 10 lakhs per year it is more than 10 lakhs per year is very difficult to sanction. Okay, 10-20 lakh जो करना कर दो well बाकी हम कर लेंगे. Okay, so this kind of attitude we also be done. Okay, yeah, that attitude is different. Okay, so academic is for the knowledge. Okay, it is not for the product and all those things. Okay, so basically, okay, so there are multiple plumes. Till I also a single plume. Multiple plume interact with each other. There is some updrafting also. Along with radiation, I made a statement that radiation is very important. Upstream thing is there. Radiation. Some when plume contamination may happen, pressure will rise and plume can updraft to the base state. And along with radiation convection, high temperature fluid can also reach to the base state and can cause heating. Okay, so this kind of results are maybe we are doing on based on whatever facilities we have and the students we have. But let's see up to what time, to what level I okay. So summary, then this comes to the end of my presentation. Okay. So whole summary is that knowledge of radiative transfer enable you to work in 3 distinct areas. And these are very fascinating areas in high engineering, aesthetic and climate. Field is under the burden of the ministers, okay, lack of academic and easy tools. And role of radiation is to modernize the temperature and reduce the temperature on 200 to 300 Kelvin.